We are going to see the chapter light. Here we are going to focus on two concepts, that is the reflection of light by spherical mirrors and refraction of light and the applications in the real life. What is light? Light is a form of energy. Okay, it helps us to see all the beautiful things around us. Okay, during daytime, the sunlight is the main source of light that helps us to see the objects clearly and visibly. Okay, so this light travels in a straight line. It enters our eyes through the pupil and it forms an image on the retina, so we are able to see the image clearly. So without light we cannot see anything clearly or visibly, so we need the presence of light to view the things clearly. So light is a form of energy that helps us to see the objects. This light consists of electromagnetic waves because it contains both the properties of electric and magnetic properties. So when light falls on objects, it reflects the light and we are able to see the objects in the presence of light. So next, the light travels in a straight line. So some common phenomena for the light are formation of the shadows, formation of the images by mirrors and lenses, then bending of light by a medium. Okay, so then twinkling of stars and formation of rainbows are some of the phenomena of the lights. Properties of light. So light travels in a straight line. The speed of the light always depends on the nature of the medium. So in vacuum space, the light travels very fast. Okay, the speed is 3 into 10 power 8 meter per second. Next, the light is a form of energy. It contains both the electromagnetic waves because it consists of both the electric and the magnetic properties and they are transverse in nature. So next, the properties are refraction, reflection, and light travels in all directions. Next, we are going to see the reflection of light. Here, when the light falls on a highly polished surface area like a mirror, most of the light is sent back to the same medium. So this process is called the reflection of light. Okay, laws of reflection of light. Here, the angle of incidence is equal to the angle of reflection. So next, the incident ray, the normal ray and the reflected ray all lies in the same plane. These laws of reflection are all applicable to all types of reflecting surfaces including the spherical surfaces. And in the formation of image by a plane mirror, we are going to see the properties of the image. So here the image is always erect. Erect means nothing but it is always in the upright or a straight position. So next, the image is the same size as the object. It is the same size as the object. And the image is at the same distance from the mirror, okay, as the object is in front of it. So this is the mirror. Here it will be of the same distance. Okay, next, the image is virtual, so it cannot be obtained on any screen. So next, the image is laterally inverted. Laterally inverted means it is the reversal of the mirror's images left and right when compared with the object. So next we are going to see about the spherical mirrors. Here spherical mirror is a curved mirror which is a part of the hollow sphere. Okay, these spherical mirrors are of two types. They are concave mirror and convex mirror. So the first mirror we are going to see is the concave mirror. So concave mirror is a spherical mirror whose reflecting surface is curved inwards. So here this is the concave mirror. So it is curved inwards. Okay. The rays of the light parallel to the principal axis after reflection, okay, from a concave mirror all meet at a point. So they all meet at a point on the principal axis. So it is converge. Next is the convex mirror. Convex mirror is a spherical mirror whose reflecting surface, this is the reflecting surface of the convex mirror. So it is curved outwards. Okay. The rays of light is parallel to the principal axis after reflection. So from the convex mirror, it gets diverged and it appears to come from a point behind the mirror. So here we are going to study some of the terms that are used in the study of spherical mirrors. Okay, here the first term is the center of curvature. Okay, it is the center of the imaginary sphere of which the mirror is a part. Okay, it is denoted by capital C. So here when we consider the concave mirror, the center of curvature lies in front of it. Okay. Then when we consider of convex mirror, the center of curvature will always lies behind it. Okay. Next is the radius of curvature. So this is nothing but it is the radius of that imaginary sphere. Okay. It is denoted by CP. So next is the pole. Pole is the center of the spherical mirror. That is, it is the pole is the center point of the reflecting surface. Okay. Next is the principal axis. Okay. Principal axis is the straight line that is passing through the center of curvature and the pole. Okay. I will explain this with the diagram in the next slide. Okay. Next is the principal focus. Principal focus I have defined here for both the concave and the convex mirror. Okay. In concave mirror, the rays of the light parallel to the principal axis after reflection all meets at the point. Okay. That is called the principal focus. Okay. In convex mirror, the rays of all light parallel to principal axis after reflection, it diverges. Okay. And it comes to form a point. Okay. This point will be found behind the mirror called the principal focus. So, okay. Next term is the focal length. This focal length is always the distance between the pole and the principal focus. So it is denoted by F. Okay. And here in the spherical mirror, the radius of curvature is twice the focal length. So the formula for the radius is 2 into F. That is 2 into focal length. Okay. Here to find the focal length, we have to divide R by 2. Okay. So here in the given diagram, the principal axis is xy. So here in this line xy, the principal axis is the line joining the pole and the center of curvature. Okay. Next is the pole. Pole is the midpoint of its reflecting surface. This is the reflecting surface and pole is in the midpoint. That is, it is in the middle. Okay. Next, radius of curvature is the radius of the spherical mirror. So next, this focal length. The focal length is the distance between the pole and the principal focus of the spherical mirror. So this is the focal length. So these are some of the terms for your easy understanding. Okay. So here we are going to see the reflection by the spherical mirrors. So we have already known that the reflection is the phenomenon of bouncing back of light rays, okay, in the same medium when it is striking the smooth surface. This is called the reflection of light. Okay, we have already studied the laws of reflection. There are two laws of refraction, and here the first law is the angle of incidence is always equal to the angle of reflection. So, okay, second law is the incident ray and the reflected, the incident ray and the reflected ray and the normal all lie on the same plane. Okay, these in reflection of light, these two laws are used everywhere. Okay, so here in the concave mirror, so okay, in the concave mirror, the rays of the light parallel to the principal axis after reflection passes through the focus in concave mirror. Okay, so when we consider the convex mirror, the ray of light parallel to the principal axis after reflection appears to diverge from the focus. Okay, so these are for both the mirrors. So okay, here in a concave mirror, when a ray of light passes through the focus after reflection, this line goes parallel to the principal axis. Okay, so when we consider the convex mirror, here the ray of light directed towards the focus after reflection, it is also parallel to the principal axis. Next is when we consider a concave mirror, and here the reflection takes place, the ray of light passing through the center of curvature after reflection is reflected back along the same direction. Okay, so same like that it happens in the convex mirror. In the convex mirror, when a ray of light is directed towards the center of curvature, after reflection it is reflected back along the same direction. It doesn't goes anywhere, it just travels along that same direction in both the mirrors. So according to the laws of reflections, we have learned that the angle of incidence, that is the angle of incidence, is always equal to the angle of reflection. So here in a concave mirror, a ray of light directed to the pole is reflected, making an equal angle with the principal axis. So here these both angles are equal. The same is to the convex mirror. So same, the rays or the incident ray, the angle is equal to the reflected ray. And now we are going to see about the image formation by the spherical mirrors. So here first we are going to see the image formation by a concave mirror. So let us consider a concave mirror. Here when the object is present at infinity, the image formed is at the focus. It is highly diminished, real and inverted. Okay, it is very diminished in size. Here the position of the image will always be at the focus or in the focus plane. So here in the second case, when the object is beyond C, the image formed is between C and F. Okay, the formed image will always be diminished, real and inverted. Okay, so here the position of image is here, it is between the focus and the center of curvature. So the third one is here the object position is at the center of curvature C. So the image formed is also at the C. So here both are of same size as that of the object. And here the image formed is real and inverted. So three things here too we have to remember, that is the real, inverted and the same size of that of the object. So here in the fourth one, when the object is between the C, center of curvature, and F, the image formed is beyond C. It is formed beyond C. Here the position of the image is beyond the center of curvature. Okay, and here the nature and size of the image here is real, inverted and magnified. It is enlarged in size when comparing the object. Okay, and next one is when the object is at F. Okay, when the object is at F, the image formed is at the infinity. So the image formed is highly enlarged in size. It is real and inverted. And in the sixth case, here the position of the object, okay, it is present in between the pole and the focus. So it is in between F and P. The image formed will be behind the mirror. So here the position of image is behind the mirror, and here the nature and size of the image will be virtual and erect. Okay, the size is enlarged when comparing to the object. And next is the image formed by the convex mirror. So here, for studying the images formed by a convex mirror, there are two positions of the objects that have to be considered. So there are only two cases. That is the first one when the object is at infinity, and the second position is at when the object is at finite distance from the mirror. So let's see that now. Okay, in the first case, when the object is at infinity, the image is formed at F behind the mirror. So the image formed will be highly diminished, virtual and erect. Okay. So in the second case, the object is present in a finite distance, that is it is in between the infinity and the pole. So here the image formed is behind the mirror, and the image is diminished, virtual and erect. So these are the two positions for the convex mirror. Uses of spherical mirror. So we are going to see the uses of the concave mirror and the convex mirror. So first we are going to see the uses of concave mirror. So here these concave mirrors are used in torches, searchlights and headlights of the vehicles to get the powerful parallel beam of lights. Okay, so second, they are used as a shaving mirror because they produce the larger images of the face, so it can be clearly seen. So next, these concave mirrors are also used by the dentist to see the larger images of the teeth, so they can clearly do their procedures. So then large concave mirrors are used to concentrate sunlight to produce high heat in a large amount in the solar furnaces. Okay, these are all the uses of concave mirrors. And next we are moving on to the convex mirrors. These convex mirrors are used in rear view mirrors in the vehicles. This convex mirrors gives erect diminished images of the objects. Okay, because they have a wider field of view as they are curved outwards. And next, this convex mirror can also be used for shop security purposes. The shop owner, he can keep a track on the customers to look whoever is there. For example, let they check for thieves or shoplifters among them. Okay, it will easily help them to find it out. Okay, so when we are dealing with the reflection of light by spherical mirrors, we have to follow a set of sign convention called the New Cartesian sign convention for spherical mirrors. So these are based on Cartesian coordinates. So we are going to see what are the conventions. Okay, so they are as follows. So the first one is the object is always placed on the left of the mirror. So it is always placed on the left of the mirror, and the light from the object falls from left to right. Okay, so second point is all distance parallel to the principal axis are measured from the pole. So the distances parallel. The distance is parallel to the principal axis or measured only from the pole. And third, the all distance measured to the right of the pole. That is, this is the pole. Here all distances measured to the right side. This is the right side. So this side is measured in positive. Okay. So likewise opposite. The distances measured to the left of the pole are taken as negative. Distance toward the left is taken as negative and towards the right is positive. So next is the height. The height is measured upwards perpendicular to the principal axis is taken as positive, and likewise vice versa. It goes when the height downwards the perpendicular to the principal axis is taken as negative. So these are all the conventions we have to keep in mind for a concave mirror. So next we are going to see the mirror formula for the spherical mirrors. So here in a spherical mirror, the distance of the object from its pole is called the object distance. Okay, and then the distance of the image from the pole of the mirror is called the image distance, and focal length is nothing but it is the distance of the principal focus from the pole is the focal length. So the relationships between the quantities, that is V, U and F, okay, is called the mirror formula. It is expressed in this form. So you have to learn, that is 1 by V plus 1 by U is equal to 1 by F. This is the mirror formula. Okay, here these U, V and F are used according to their Cartesian sign conventions. Okay, this formula is valid. This formula is valid in all situations for all spherical mirrors. Okay, in whatever positions the object is present. Okay, next is the magnification for the spherical mirrors. So the magnification of the spherical mirror is nothing but it is a ratio of the height of the image to the height of the object. So magnification is denoted by M, and height of the image is considered as HI because of image I. So height of object here HO. So the magnification is also related to the object distance and the image distance. Here it is expressed in the form magnification is equal to M. It is denoted as M, and here it is given as H of I by H of O is equal to minus of V by U. Next is the identification of the mirrors. Okay, here by observing the images produced by a mirror for different position of objects, the nature can be easily identified. So suppose here the focal length of the spherical mirror is always independent of the medium in which it is present. So here let us consider. So when the image formed by the mirror is of the same size as that of the object, then it is said to be a plane mirror. Okay, so next case, the image formed behind the mirror is longer than the object, means then the mirror is a concave mirror. So third, if the image formed by the mirror is always diminished wherever position the object is present, then the mirror is said to be a convex mirror.